Hello and welcome to another video. Let's look at this physics question about the refraction of light, which is one of the topics in geometrical optics. Of course, we know that refraction of light means the bending of light at the interface, just like what we have here, separating two material media with different velocities of light or different optical densities, or with different what we call indexes of refraction. So just like what we have here, light passes from this transparent medium into this other medium. Okay, that is the second transparent medium. So when light is transmitted obliquely through the boundary surface separating two material media with different what we call optical densities or different velocities of light, then the phenomenon of light, okay, transmitted obliquely through the boundary separating two material media with two different velocities of light or optical density, also known as indexes of refraction, is what we call refraction of light. So in this question, okay, we have that a ray of light traveling through air is incident at A. So we have, this is the first boundary. So the light ray, okay, which passes from this medium into this medium, this is air, then it passes into liquid with index of refraction 1.35. Okay, so we have that a ray of light traveling through air is incident at A, okay, at an angle of 50 degrees to the glass. So which means the angle which the light that hits the boundary at A, okay, makes with the surface is 50 degrees. All right, so which means first we have, okay, the first item we have there will be incident angle. That is, we have angle of incidence. So at A, we have angle of incidence. Okay, we have angle of incidence. So that will be theta I, and that equals to 50 degrees. Onto a glass. This is the glass, okay, a glass surface which is coated with a layer of liquid. Okay, use the information given below to find the angles of x, to find the angles x and y. Absolute refractive index of liquid equals 1.35. Absolute refractive index of glass equals 1.52. Now we can see what happened here. The light passes from air into liquid. The refractive index of air is 1.0. Okay, so light passes from air into liquid having a refractive index of 1.35. Then from liquid it passes into glass, okay, of refractive index 1.52. Okay, now in this case we observe that when the light passes from air into liquid, okay, we observe that the refracted ray, okay, makes an angle x with the boundary. This is the boundary or the interface. Okay, then the refracted angle, which is angle of refraction x degrees, okay, will be equals to, it will be alternate to this other angle here. So which means, because we are given here that assume flat parallel layers, so because of the parallel layers, so this means that the angle of refraction at A, okay, will be equals to the angle of incidence at Y. B. So our task is to find the angles x and y, okay, in this question. So first at A we have angle of incidence to be 50 degrees, and we're also giving index of refraction, okay, of air, which is our NA, N subscript A, to be 1.00. Okay, now so that's when we talk about the light passing from air into, as it passes from air into liquid. Okay, so air is the first medium, so liquid is the second medium. So when light traveling in air, okay, strikes the boundary or hits the boundary, then it will bend you can see here it bends away from the normal. That is because the second medium, okay, has high optical density. That is, it is denser, it has more, the refractive index of the second medium is higher than the refractive index of the first medium. Okay, so from which the light came. So we have index of refraction of air to be this. Okay, so now this is liquid. This is the angle of refraction in liquid. So we can then say that for liquid, okay, so for liquid, we want to calculate x. So to calculate x in this case, so we know that angle of refraction, angle of refraction, angle of refraction, okay, angle of refraction, that will be x. Okay, then we have refractive index of liquid, refractive index of liquid. This is equals to, so which is this, and it equals to 1.35. So this is when we can now apply the Snell's law of refraction. That is, Snell's law states that the ratio of the sine of angle of incidence to the sine of angle of refraction, that will be proportional to the what? To the reciprocal of the absolute index of refraction. Okay, that's the absolute index of refraction measures the ratio of the index of refraction of one material medium with respect to another medium. All right, so which means we're going to apply the Snell's law. So applying the Snell's law at A. So which means we're going to have, that is, we have the refractive index of air, okay, multiplied by sine of angle of incidence equals to the refractive index of liquid multiplied by sine of angle x, which is angle of refraction. Okay, so in this case, we want to calculate the value of x. So we can then write, this will be sine x equals to index of refraction of air multiplied by sine of angle of incidence divided by the refractive index of liquid. All right, so let's plug in the value. So in this case, this will be sine of x equals to, in air, we have 1 multiplied by sine. So we have here that the angle of incidence equals 50 degrees. So this will be sine 50 degrees divided by, then the index of refraction of liquid. That will be, the index of refraction of liquid is 1.35. Okay, so that this will be sine x equals to, now let me get the value for sine 50 degrees. So now sine 50 degrees, that will be 0.766 divided by 1.35, 1.35, so that this will be sine x equals to 0.5674, so that the inverse sine of 0.5674 will be equals to x. Okay, so x equals to inverse sine of 0.5674. So let's get it. What is inverse sine of 0.5674? That will be, so this is x equals to 34.6. Then we can approximate this to be 35 degrees. So the value of x is 35 degrees. Okay, the value of x is 35 degrees. Now, so this is when we apply the Snell's law at A. Now, like I said, you know, now the angle of refraction at A will be equals to the angle of incidence at B. That is because we have parallel layers. Okay, so just like when we apply one of the theorems in plane triangles in mathematics, we know that this is alternate angle, okay? Interior alternate angle, okay? So now, so in this case, which means the value of x, okay, the size of this angle will be 35 degrees. So now let's consider, let's now apply, I'm going to apply the Snell's law at B, okay? I'm going to apply the Snell's law at B so that we can find the value of y. All right, so applying, now let's calculate y. So applying or apply the Snell's law at B. Applying the Snell's law at B. So we have that. So in this case, this is going to be, so at B, this is when we have liquid glass interface. But at A, we have air liquid interface. So in this case, the interface we consider in this case, this is in the case of, let me write it here, we have, this is in the case of air liquid interface. Okay, so this is in the case of air liquid interface. All right, so in this case, this is when we talk about liquid glass interface, because the light passes from liquid into glass. So the bending ray, which is the refracted ray, makes angle y with the what? With the boundary or the interface, because of course we know that that's phenomenon of light bending at the interface, separating two material media with different indexes of refraction or different optical densities or with different velocities of light, is what we call refraction of light. All right, so applying the Snell's law at B, so we then have the index of refraction of the liquid multiplied by sine of angle x, this angle, that will be the incident angle. Then this will be equals to the index of refraction of the glass, this guy, multiplied by sine of angle of what? Refraction, and that will be y. So remember, the light passes from air into what? Into liquid with refractive index 1.35. So let's not forget that that is because when light is obliquely transmitted, okay, through the boundary separating two material media with different velocities of light or different optical densities or with different indexes of refraction, that's when we talk about what we call refraction of light. Okay, so this guy is 35 degrees, or I'm going to use 34.6. Okay, so we can then write, I'm going to write, we have n subscript L sine x equals to n subscript G sine y. So this is 34.6 sine, okay, so the index of, this is the index of refraction of the liquid, which is 1.35. Then we know that the index of refraction of the glass is 1.52. Okay, so this would be index of refraction of the liquid, which is 1.35, then sine 34.6 equals to 1.52 multiplied by sine y. Let me write this again. We're going to have this to be 1.35 sine 34.6 equals to 1.52 multiplied by sine y. Okay, so let's get the value of y. So first, I'm going to make y the subject of the formula, so that this will be sine y equals to 1.35 sine 34.6, then divided by 1.52. Okay, so first, let's get the numerator. 1.35 multiplied by sine of angle 34.6. So that will be 0.7666 divided by 1.52. So this is still equals to sine y. So dividing 0.7666 by 1.52, okay, we're going to have sine y to be equals to 0.5043. Now, to get y, so we're going to have y to be equals to the inverse sine of 0.5043. Okay, so we have inverse sine of 0.5043, and that equals to y equals to 30.3, and this will be y will be approximately equals to 30 degrees. So therefore the value of x is 35. Okay, x is approximately 35 degrees. Okay, and then y is approximately 30 degrees. So these are the values of x and y. The noblest pleasure is the joy of understanding. Bye bye.